So this video is about polyprotic acids. So we've already learned a little bit about polyprotic acids. And what we want to do now is be able to think about how we would do pH calculations with polyprotic acids. Remember, we've got all this theory, and so it might be nice if we can make predictions with that theory. So now we understand a little bit about polyprotic acids and bases. We would like to calculate the pH of a solution. Here is an example of a polyprotic acid. This is sulfuric acid, H2SO4 right here. And so it donates its first proton, highlighted here in red, to water and makes hydronium and hydrogen sulfate, right here, HSO4 minus. And the acid dissociation constant, we call it Ka1, for this reaction is much, much greater than 1 because we know sulfuric acid is a strong acid. In fact, it's been measured in certain ways to be about 2 times 10 to the power 6. So yeah, 2 million is much, much greater than 1. Now what we can do is donate the second ionizable proton from HSO4 minus, hydrogen sulfate, to water to make hydronium and just regular old sulfate. And the Ka2 for that dissociation is 1.2 times 10 to the minus 2 at 25 degrees Celsius. So this second proton, its acidity, we would consider it a weak acid. Now it's not as weak as some acids we've seen. So look at this exponent over here, 10 to the minus 2. So that's certainly less than 1, but it's not fantastically less than 1, like 10 to the minus 5 or 10 to the minus 8, or some other kinds of Ka values that we've seen before. By the way, I should mention that it's easy to look up Ka values in tables. Most chemistry textbooks have a table of a whole bunch of different kind of acids and their various Ka values in the back of the book. You can also find them online all over the place. So what we would like to do now is answer a question kind of like this. We would like to know, okay, suppose you have a 0.1 molar sulfuric acid solution. 0.1 molar sulfuric acid solution, and we want to know what's the pH of that solution. Now with strong acids in the past, like if this were a 0.1 molar HCl solution, we would just say, hey, HCl is a strong acid. So it completely dissociates. So if I have 0.1 mole per liter of HCl, it's going to dissociate to give me 0.1 mole per liter of hydronium. And then I can just take the negative log of 0.1 and get the pH. But with sulfuric acid, I might worry about the second proton coming off at least a little bit. This doesn't happen very much, but at least a little bit to increase my H3O plus concentration. So we might want to handle that. So here's how we do that. So I'm going to work through this problem. So I told you there's an easy way to figure out the concentration of hydronium from this first dissociation, and that's just to use the stoichiometry that it's 1 to 1. So if you have 0.1 mole per liter H2SO4, you'll get 0.1 mole per liter H3O4. But just to make that clear, I'm going to write that out as an ice table. Now you might not have to do this ordinarily because you'll know that, oh, it's a strong acid so it completely dissociates. But this is just so we can see where it all comes from. So I'm going to rewrite this first equation up here, and we're going to make our ice table. So here's my equation. Sulfuric acid reacts with water, just like I've copied from above. And we're going to construct our ice table now. So I'm going to scroll down so we can have a little bit more room here. Initial, change, equilibrium. So initially I start out with 0.1 mole per liter. And I'm going to leave off the labels from now on. And we don't care about the water. And we don't have any hydronium or any hydrogen sulfate to start with. And so the change. Now normally in this change column we would write minus x, right? Because we don't know how much is going to go away because it's an equilibrium. Well, in this case we know it's 100% dissociation. So how much is it going to change? All of it. It's all going away. So minus 0.10 molar. And so if it's minus 0.10 molar here, then because it's 1-to-1 stoichiometry, if we lose a tenth of a mole per liter over here, we're going to gain a tenth of a mole per liter over here. So our sort of plus x, well, we know what x is, it's 0.1. So we get plus x for both of these, plus 0.1. All right, so then we add down the column. We have no H2SO4 left. We have 0.1 mole per liter of hydronium and 0.1 mole per liter of hydrogen sulfate. Okay, so that's the first step. Now I told you we need to worry about this HSO4 minus. So now we're going to do that again. We're going to make a second ice table. So I'm going to write down the dissociation reaction for the second ionizable proton right here. Okay, so here's that reaction. Hydrogen sulfate donates a proton, just like we talked about. Here's the Ka2 value. So we're going to make another ice table. So to really work this problem correctly, we're going to need 2 ice tables. And the reason is that second ionizable proton is kind of weak, but it's getting close to being stronger, so we might want to account for it. Let's see how much we get. So now we're going to fill in our initial values. So do we have some initial HSO4 minus? Oh, well now we do, yes, because after this first step, this first ice table up here, you see that we've made some. So I'm going to copy that down here, that we start out with 0.1 mole per liter of HSO4 minus, because we fully dissociated that sulfuric acid from our first ice table. Again, we don't care about the water. Do we have any H3O plus initially? Now, usually we're used to writing 0 here, but now notice from our first ice table, aha, we have 0.1 mole per liter of hydronium already. So I'm going to put that in there, 0.1 mole per liter. And we don't have any sulfate, SO4 2-, because none of this HSO4 has dissociated yet. Okay, so now there's going to be a change. How much? Well, we don't know, because this is an equilibrium. So we're going to say minus x. So if we lose x there, we have to gain x over here. So plus x plus x. Then we add down each column. This is 0.1 minus x, 0.1 plus x, and x. So now we know our E-line values right here, and they get substituted into our equilibrium constant. So let's make some more room down here, and let's do the math. So we've got Ka2, which is products over reactants. So there's our acid dissociation constant expression for this reaction. And we know that equals 1.2 times 10 to the minus 2. So let's substitute in my E-line values, because these concentrations are equilibrium concentrations, because this is the Kc, the equilibrium constant for this reaction. So products are 0.1 plus x and 0.1 minus x. And that's supposed to equal 1.2 times 10 to the minus second. Now we have an algebra problem to solve. We want to solve for x. Sometimes we make this small x approximation where we neglect x. So to do that, we need to assume that this reaction doesn't happen very much in the forward direction. And usually what we look at is that rule of 1,000 or 100, I can't remember. Anyway, you go back and check the video. So we look at that rule and we compare this sort of exponent to this value right here. And if they're very different, then our assumption's probably going to be good. But the difference between 0.1 and 0.01, which is 10 to the minus 2, not that different. So probably our approximation, our small x approximation, is not going to be good here. So it looks like we're going to have to bite the bullet and solve the quadratic equation here. I'll not go through that right now, because you've seen how to do that before. So we're going to grind through the quadratic equation. Multiply through by x here, multiply both sides by the denominator, and solve for x. So you could plug this into a solver program like on Wolfram Alpha and just ask it to solve for x. Or you can grind through the quadratic equation and substitute in like you know how to do. But anyway, when we do that, we solve. We get x is equal to either 0.010 or negative 0.122. Alright, so having an x value, an E-line value right here of sulfate concentration that's negative doesn't make any sense, right? You can't have negative concentrations. So that answer is bogus. So we can't do that one. So we're going to pick this other concentration as the one that we want to use for x. And so now we can finish our task, which is calculating the equilibrium hydronium. So this is what we have from our first dissociation reaction. And so from our second dissociation reaction, we get a hydronium ion concentration of 0.1 plus x. So 0.1 plus x. So what is x? X is 0.01. So that gives us a final concentration of 0.110. So you see, if we had just taken our first dissociation, we would have missed this hundredth of a hydronium ion molarity here that contributes to the hydronium ion concentration. So our pH would have been in the ballpark, but off a little bit. Now I should mention that in fact we are already making some approximations with this 2 ice table approach, but it's a pretty good approximation. Normally we would say that we have sort of actually several simultaneous equilibria to solve, and that's a more advanced sort of math problem. And if you take an advanced chemistry course, like say in quantitative analysis, chemical analysis, you might learn about how to do those kind of more advanced problems. Anyway, so this is our final concentration. Now we want to calculate the pH of that, so we can get the pH of our sulfuric acid solution. So pH is going to be the negative log of that number, negative base 10 log of that number. And so we get a value of 0.96. So there's our pH. And over here it looks like probably we really just have two significant figures, so this one is not correct. And since we have two significant figures in this number, we're going to have two decimal places in our answer when we take the pH. So there's our final pH, and that's how you calculate the pH of a polyprotic acid system. Now, I should tell you that many times we'll have a polyprotic acid where our acid dissociation constants are all really small and all fairly different from each other. So, for example, if we look at sulfurous acid as opposed to sulfuric, so that would be H2SO3. So here's sulfurous acid, H2SO3, first dissociation, we lose a proton, we make hydrogen sulfite over here, HSO3 minus, and that has an acid dissociation constant of 1.7 times 10 to the minus 2. So this is a weak acid. So we're only going to get a little bit of H3O plus from this first dissociation step. But this is also a diprotic acid because we have two protons right here, so both of them could come off, and so we could donate our second proton from HSO3 to water, and we make these products, hydronium and sulfite. And the acid dissociation constant Ka2 for this reaction is 6.2 times 10 to the minus 8. So that's a pretty small number. And notice if we just look at the powers here between these two guys, so the power here, 10 to the minus 2 and 10 to the minus 8, these are very different. If they happen to be different by more than about a factor of 10 to the power 2, so if you see a difference of 2 or more in these two numbers, then probably you really don't need to account for this second dissociation. So remember in that first problem we had to set up two ice tables. Well, in this problem we're just going to use this first reaction to set up our ice table. So we're just going to do an ice table with our first reaction, and we can omit the ice table for the second reaction because this Ka2 is so much smaller than the Ka1. So very often you will see that you can do a pH calculation on a polyprotic acid just by considering the first step, because the second step is going to contribute, a tiny fraction more H3O plus, and so it's going to be way out here, 0.10000, and then you'll get a little bit more hydronium, and that's really not going to change your pH in any significant way once you calculate it. So we can ignore that part. So we'll ignore those dissociations, the subsequent dissociations, and if you have a triprotic acid or something even more unusual, then you might have several deprotonation steps, and we can omit all of the other ones because they're all going to be much smaller. Remember that the Kas get significantly smaller as you go down. So that's how we calculate pH of polyprotic acid solutions.